This is one of the legs in USM, a leg that forms part of the balance of the local ecosystem. But do you all know what inside this leg? If not, how do we want to know what's bottom of this leg? What's for the great ocean? And how we want to explore the deepest ocean? Mariana Trench, for the example. First equipment comes to our mind is Echosounder. Echosounder is an underwater scanning device that can scan in lakes, rivers, and even seas. Echosounder is a device for determining the depth of the seabed or detecting objects in water by measuring the time taken of sounds, echoes to return to the listener or receiver. When mounted on the vessel, this device is generally termed as photometer, and when mounted on the submersible, it's termed an altimeter.
The first patent for an echo-sounding device was granted in 1907. The photometer, a registered trademark often loosely applied to all depth sounding gear, was developed in 1914. As a result of the research by the Canadian engineer R.A. Fessenden in application of echo-sounding principle to iceberg detection. Application of echo-sounding principle to submarine detection during World War II resulted in the development of equipment to scan all ocean depths. In 1954, an advanced and highly accurate echo sounder on that time, called the Precision Depth Recorder (PDR), was developed. By the early 1690s, the US Navy used the sonar array survey system to map large swaths of the ocean floor to assist the underwater navigation of each submarine force. SASS was tested aboard the USS Compass Island. The final array system, composed of 61 to 1 degree beam with a swath width of approximately 1.15 times water depth, was then installed on the USNS Bowditch, USNS Dutton, and USNS Michelson. Starting in 1970s, companies such as General Instrument developed systems that could be mounted to the hull of large ships and small boats. The first commercial multibeam is now known as the C-beam Classic, was put in service in May 1977 on the Australian survey vessel HMS Cook. As technology improved in 1980s and 1990s, higher frequency systems suitable for high resolution mapping in shallow water were developed. Multibeam Echosounder are also commonly used for geological and oceanographic research, and since the 1990s for offshore oil and gas exploration and seafloor cable routing. The National Oceanic and Atmospheric Administration has recently used an unclassified version of SASS and C-beam to map more detailed representation of the seafloor. C-beam employ an array of sound transducers across the hull of the survey vessel which radiates sound in a swath, thereby allowing the wide region of the seafloor to be mapped. Nowadays, there are two major types of echosounder, which is single beam and multi-beam. Single beam echosounder is measure the double wave transit time of an acoustic signal reflected on the seabed. Water depth under the echosounder base is computed knowing the sound velocity in water. Single beam system typically have a beam width of 10 to 30 degrees and estimate depth by measuring the shortest length range to the seafloor within the main beam. In addition to the single beam echosounder, there are Echosounder that capable receive many pings. This is what we call is multibeam echosounder. Multibeam echosounder is a type of sonar that is used to map the seabed. Consists of more than two beams attached to the one sonar head. Like other sonar system, multibeam system emits sound wave in the fan shape from the sonar head. The amount of time it takes for the sound wave to bounce off the seabed and return to the receiver is used to determine water depth. Unlike other sonar, multibeam system use beamforming to extract directional information from returning sound wave, producing a swatch of depth reading from the single beam. A multibeam echosounder is a device typically used by the hydrographic surveyor to determine the depth of water and the nature of the seabed. Let's go to see how multibeams works and how the multibeam interpret the data. In this case, the functioning of R2 Sonics 2020. For this kind of model, there are three main components of multibeam that we need to know, which is data collection computer, sonar interface module, and sonar head. These three components will be set up on the ship. The sonar head must be mounted to both, and there are three types of mounting, which is over the side mount, moon pool mount, and hull mount. The other one is ROV mounting. The over the side mount is normally employed for the shallow water survey vessel or temporary survey requirement. The over the side mount consists of a frame structure that attached to vessel hull and or superstructure. A pole will be attached to the frame, normally through the use of swivel flanges, or the other means by which the head can be swung up when not in use and deployed when it's needed. A similar mounting arrangement is a bow mount, which is specialized form of over the side mount. In order to ensure stability of the pole, it should have skewering arrangement as close to the water line as possible. The head should be washed with fresh water as soon as possible and inspected for any damage or marine growth. If the head is remain up position, a covering should be put over the head to protect it from the sun. Deploying the sonar head through the moon pool is usually a more stable mounting arrangement than an over the side pool. A moon pool is an area within the vessel is open to the water. The sonar head is normally mounted in such that way can be deployed and recovered through the moon pool. The pole or structure that sonar head is mounted on the normally shorter and steadier than over the side mount. This can allow for the higher service speed. The hull mount is the steadiest all possible way to mount of sonar head. With the hull mount, the sonar head is physically attached to the vessel hull. With this way of securing the sonar head, there is no possibilities of movement outside of the movement of the vessel. But there are some disadvantages for this kind of mounted. The head cannot be inspected easily for marine growth or damage, and the vessel may be restricted in the depth of water that can be surveyed due to the head being permanently attached to the hull. A normal hull mount will also involve the fabrication of the fairing on the hull to ensure the correct flow pattern over the sonar head. The last mounting is ROV, which is this new mounting. The Sonic 2024 is the ideal for the undersea operation due its compact size and lower power consumption. As all processing is done in the receive module, all is required is to provide a single mode fiber optic communication between the SIM and the receive module. The 48 VDC can come from the surface or supply via the ROV-ON's power distribution. Okay, now let's go to the how exactly the multibeam sonar works. This system works by transmitting a sound pulse called a ping through the transmitter at the specific frequency and then receive the same pulse through the receiver placed very close to the transmitter. The transmitter and receiver are called transducer because they convert energy into another form. The transmitter converts an electrical signal into the acoustical pulse and the receiver converts an acoustical pulse into the electrical signal. A computer determines how long it takes to receive the returning pulse, which is when the transducer are pointed toward the seafloor, translate to the depth. The more time it takes for the pulse to return, the farther away the object is. Assigning color range or grayscale for the depth can create the topside view of the seafloor. Multibeam has several transducers that allow a large swath of area to be surveyed at once, making surveying much faster and more accurate. The swath width is determined by the depth of the seafloor being surveyed. The ping is emitted in the fan shape outward from the transmitter. The farther away the object, the more area there is the sound to echo off. The sonar ping several times per second, which with the speed of both determine the horizontal resolution of the image created. If the boat moving very fast and the rate of the sonar unit is pinging slow, then the number of times sound is bound off the seafloor in the area covered is few than if the boat moving slower while the unit was set up to the higher ping rate. Also, if the area being covered is very deep, then the boat must be more slower over the area, or the unit must be set up at the higher ping rate in order to achieve an equal quality image to the image at shallow depth, because it takes longer for the sound pulse to return to the transducer. The ping rate is also limited by the speed of sound in water, because with most multibeam systems, the transducer must wait to receive the last ping sent before generating the next one. This operational constraint sets an upper limit on the ping rate for the given water depth and swath width combination. Bending of the ping path through the water due diffraction is another source of error that must be corrected. The speed of sound in water varies with the water density, which is dependent upon salinity and temperature. Water of different density tend not to mix, and they form discrete layer, resulting in what is known as the esterified water column. This phenomenon is responsible for the thermocline swimmer experience when they are dug below the surface and find the layer of cooler water. This layering causes of the speed of each ping change, and its parts bend a little bit every time it's passed through the density change. Without correction, this speed change and bend would result in the multibeam system inaccurately calculating when the ping hit the seafloor and distance is traveled. To correct the reflection error, hydrographer must stop and do sound velocity profile (SVP) cast every couple of hours during the survey. They do this by lowering the sound velocity profiler to the bottom and backlogging to the depth and sound velocity. Numerous fields require access to the seafloor topography and geomorphology. The onboard deep sea multi-beam sounding system should be used to map the area and obtain a relatively accurate topographic map of the seabed to provide basic train data. Although the ship-borne deep sea multi-beam sounding system can detect a wide range of deep seabed terrains, and its detection accurately limited, and it cannot search for the small object on the seafloor. Underwater vehicles such as DT, AUV, ROV, and HOV can carry more high-frequency multibeam to near seafloor to achieve accurate topographical detection. The corresponding multibeam is designed with a special pressure-resistant design with pressure depth of up to 6,000 meters or even deeper. Near seafloor micro-topographical mapping is a significant supplement to full sea depth topographical detection. It combines micro-topographical mapping sonar with underwater vehicle and can dive to near seafloor to achieve accurate topographical detection. DT and AUV are more suitable for the large area micro-topographical mapping survey, owing to their good streamline and control stability. However, although the mapping and detection results are affected by other factors, ROV and HOV are still needed for the small site micro-topographical mapping. Due to multibeam high degree of precision and accuracy achieved by the time stamping each transmitted ping and precisely measuring the time and the angle of its return, it is possible to create stunning three-dimensional surface model of the seafloor. These images are of such high resolution that a topographic formation of the bottom or even man-made objects such as shipwreck appear as a sharp 3D image. In order to obtain this level of accuracy, an initial motion unit IMU keeps track of the sonar transducer position several times a second using GPS and measuring the pitch, roll and heading of the boat within 200 Hz. In the future, we hope it can be better equipment to be used in ocean exploration. For now, I can see that underwater vehicle can be the best choice to achieve this purpose.